Hello, good afternoon, good morning, depending on where you are. The webinar will start in just a couple of moments. Okay, we are at the top of the hour, so let's begin. I want to start with, before we do introductions, with some webinar logistics. This webinar will be recorded. It will be made available through our website, and if you registered, you will get a link to it. We're about 40 to 45 minutes. All participants will be muted. If you do have a question, please put it into the chat engine within the webinar tool, and we'll address them towards the end. If you're having issues with audio, please press the question mark within GoToMeeting and take their advice within that workflow. Anyway, again, good afternoon. My name is Neil Batterby. I am your host in today's webinar. Continuous improvement is not a new concept in manufacturing, but even with so many methods and approaches, there's no guaranteed success in implementing continuous improvement practices. In this session today, I'm having a conversation with a leader at Saft Batteries, and she runs the continuous improvement team with great success. The Chaos team, and more on that name later, has annual operational savings targets and relies on data to get to the root cause of problems and relies on that data to validate the ROI and business case. So let me introduce you to Jill Parisha of Saft Batteries. Hi, Jill.
Hi, Neil.
So Saft is a global battery company like no other, right? I think you have employees in 49 countries, including some of the most formidable talent in that space. Saft is the preferred battery supplier for some of the world's most demanding sectors. In Cokesville, Maryland, which is where Jill is based, they make the most powerful lithium-ion battery cells that are used in markets for renewables, marine applications, satellite batteries, and something we'll talk about a little bit here is racing batteries too. Jill, would you mind providing a brief background around your journey within the Saft organization?
Absolutely. So I was initially hired as the space quality engineer, so responsible for driving root cause investigations and corrective actions for our space assembly and space testing areas. So our biggest goal was to produce what we refer to as perfect product. So those are space batteries that are built and tested without non-conformances. I came with a background in Lean Six Sigma, so I had started applying Lean principles to the problem solvings. Ishikawa or fishbone diagrams, along with generous application of the 5Y method. These two went a long way towards making it harder to repeat our non-conformances. So one of the things that it's critical about lithium-ion cell manufacture is that safety is vitally important. So the chemistries that we use for high power delivery are delicate. And when cells come through the test lab, that's the first time those cells are checked to the extremes. infant mortality is something that we want to catch and diagnose before the products go to the customers. One of these unexpected disassembly events occurred, and I spent the next 8 months in a conference room, finding, summarizing, and presenting build and test data for all the components of the product, from the raw materials that went into the electrode to the test results of the final batteries. Most of that data was on paper, and what was in one of our many databases had to be cross-checked for accuracy and then linked together. So this trial by fire meant that suddenly I was the expert on the plant's data systems, or lack thereof, and I had a good working knowledge of all the processes that output that data. So when that big effort wrapped up, I took over the management of the battery test lab, which is the culmination of all of assembly's efforts. A battery isn't a battery until it can pass test. So when I was ready for a new challenge, I worked with my boss to outline a team to spearhead our transformation from paper to digital.
Excellent. That's what we're going to talk about somewhat today. One thing that I do want this audience to know about Jill is that she's an avid Formula One fan, race fan. And it does probably help that the SAFT team in Cockeysville makes the lithium-ion batteries, like I said earlier, for many Formula One teams. It delivers kinetic and heat energy recovery systems, or KERS, right? So Jill explained to me that in layman's terms, KERS is the energy that is created during braking. It's then stored in the SAFT battery and then is made available to the motors at the wheels during the key points in the lap, such as trying to overtake. Is there anything else you'd like to add, Jill?
So the cell chemistries that we've developed for high performance racing grew out of our defense work on the Lockheed Martin F-35 Joint Strike Fighter. But due to the competitive nature of the racing series and their continual need for annual improvements, soon made this market a leader in battery performance that we actually fed back into other areas of our business. As an F1 fan, every time I see a car during a race with that blinking red light on the back, I know the battery is getting charged for future power delivery. It's exciting to know that I've been part of that system.
I'm sure it is. I'm sure it is. And I believe that the teams have had great success with this additional power plant.
Yeah, there have been. There are several teams running with our batteries, but due to the competitive nature of the industry, I can't say who.
Yeah, drat. Okay. So having spent much time with the SAFT team, I know that they have a theme of naming projects and teams with kind of Greek mythological references. So coming from the Greek word for abyss, chaos comes from the dark realm of energy, which is all that's powerful and all that is bad and evil. And I know, Jill, I've worked with your teams both here in my offices and on your production floor. They certainly all have power, but they're definitely not evil.
We take a more practical approach. Chaos is an acronym for what the team actually does. The key part of our acronym is operations support. While we are building the infrastructure to get the data we need to perform analytics, but when push comes to shove, supporting our operation team and building the products is the most important thing we do.
Okay, so what skills do you look for when you're building out your team?
So we look for a solid mix of data analytics, IT, and manufacturing engineering. So I recruited people from our test and process engineering groups, people who have experience with our systems as they stand now, and an understanding of the underlying processes that provide that data. So we're focused on data quality, data management, and then making that data work hard for us. Each continuous improvement project that we do must deliver a solid return on investment. We have to justify each project and essentially pay our own salaries through cost savings.
Okay, that makes sense. Another customer recently told me that continuous improvement organizations must be profit centers, not cost centers.
Yes, all too often these organizations are established with little thought about how they'll function with the rest of the organization. As a result, the continuous improvement organization goes about aimlessly improving with no real bottom line results from that effort. So no results means no buy-in. No buy-in means no resistance to change. And then resistance of change reinforces that lack of results.
Yeah, in previous careers, I've seen teams get very frustrated and discouraged without any documented real results for their efforts. Often if the process improvement initiative fails, the management moves on to the next thing, people become even more cynical, right? Because they think they're just moving on to the next flavor of the month. Can we move on, Jill, and just take a look at one of your key inspirations that your team identifies with as a kind of a baseline for continuous improvement initiatives?
Yeah, so a lot of our work is based around reducing manual entry and inspection. Manual tasks are generally performed at 80% accuracy, and this number is backed up by, you guessed it, data. So for our cell operations, there are 6 major routing steps. So that's 6 big opportunities with a 20% chance of doing it wrong. Every time we fill a cell wrong, zap it wrong, or form it wrong, there's a chance that it can be reworked, but more than likely it becomes scrap. And with our customer base, being able to prove that we have filled it, zapped it, and formed it correctly is almost as important as doing the work itself. When you add in our traceability requirements, that manual process list gets a lot longer, and that's a lot of opportunities for error.
Yeah, I've heard that a lot recently with our customer base, right? Being able to prove that you have done the operation, completed the inspections, checked all those boxes is almost as important as doing it right. So it's good to hear you say that. So I'm excited to for you to walk me through some of the tools, techniques, and approaches that the Chaos team uses to kind of chip away at that 20% of activities that are most likely to be executed incorrectly. And I'm sure our audience on the webinar do too. So let's go.
So there are several problem-solving methodologies, and each is adapted to the complexity of the issue and to a level of project problem management review, PMR. So step 1 is to start with a good definition of the problem. So we're all manufacturers. At each step of the production process, we add value to the product. Each operation has a standard way of work, a standard operating procedure, instructions, machine parameters, etc. A problem can be a gap or a deviation versus a standard, or that there is no defined standard.
So I know that you leverage a multitude of problem-solving methodologies, and I'm sure our audience would love to understand how you kind of match the tool to the particular problem.
So first, it is mandatory to ask if there's any risk to the people and the customer. So alerting to any risks of safety, quality, delivery, and putting containment actions in place first is key.
Okay.
And from there, we look at a really simple tool to help describe the problem. And that's the 5 W's and 1 H. That's who, what, where, when, why, and how. So the better defined the problem statement is, the more efficient the problem-solving process will be. And from there, we usually start with the 5 whys to drill into the problem definition. If we answer with an impression, the team's got to prove that with facts. If the real root cause is not identified with 5 whys and the real corrective action is not identified with this quick and simple process, then we escalate to the 8D-A3 process. In my time here at SAFT, we've had several problems that require a full Six Sigma approach. But generally speaking, 8D to A3 is the most widely used tool by my Chaos team. And this format has the added benefit of becoming a formal project.
Okay. Can we take a look at a real example, Jill, and discuss the components that go into making the 8D A3 process successful?
Well, before we look at a real example, this graphic is a good introduction to the methodology. The 8 disciplines of problem solving, or 8D, is a problem-solving methodology designed to find the root cause of a problem, devise a short-term fix, and then implement a long-term solution to prevent recurring problems.
From what I remember from my studies at university, 8D-A3 was developed by Ford Motor Company, and it's obviously very popular among manufacturers because it's effective and reasonably simple and easy to teach teams.
Yeah, the easiest way is to share how SAFT uses 8D or A3 and for us to walk through an example.
Okay, let's walk through an example.
So when it's clear that the product is defective or isn't satisfying your customers, an 8D is an excellent first step to improving quality and reliability. I will say that this SAFT template has been modified and made our own, but the fundamental disciplines are still in place. So we start up at the top left with forming a cross-functional team with subject matter experts in product, process, and data. The leader and the sponsor are critical roles. These are people who can affect change by agreeing with the findings and then provide approval and recommendations. From there, we go to D2, describing the problem using data. So the chaos team will leverage the previously discussed 5 whys, or in this case, a fault tree analysis, to define the current situation.
Okay, so there's quite a lot of detail that goes into this. What's the typical duration of an AD project with your chaos team?
So we typically have 5 projects running consecutively, with the typical project lasting between 8 to 16 weeks. There are a few projects that are longer in duration, and we tend to break those down into phases so that we can get improvements onto the floor faster. The general goal for our project is 3 hours to scope, 3 days to plan, and 3 months to implement.
333, got it.
So depending on the priority of the problem, this leads our team to D3. That's the development of an interim containment plan and a method to measure its effectiveness and avoid any additional customer dissatisfaction. So this ensures that we can balance our workload. From there, we move on to the 4th discipline to understand the root cause to enable us to take permanent action and eliminate it. The root cause always has to be validated with data. Now, our expanding use of the ShopView MES has provided us with good quality data in support of this one. Developing and reviewing the process flow diagram helps us to discover the escape point, or the closest point in the process where the cause could have been found but was not. It's not just that we should solve the root cause, but we also need to solve the lack of detection or move detection earlier in the process, closer to when the problem was generated. From there, it's the 5th discipline, the permanent corrective action directed towards the root cause and changing the conditions that were responsible for the problem. We typically perform a risk assessment and identify mandatory requirements and separate those out from wants. Discipline 6 is about effective project planning for implementation, communication, and validation of success criteria. And then we get to D7, preventing reoccurrence. In this case, it's a project closure checklist that makes sure that SOPs and control plans have been updated. We include sign-offs and approval by the core team at this stage.
I see up there on the top right, Jill, you have a business case and ROI calculations in D8.
Yeah, so traditional D8 is closure and team celebration. And remember when I said earlier, we have to pay our own salaries through validated projects? Mm-hmm. This is where we document the savings, and when executed well, we celebrate our successes.
Okay, great. Before we move on, I understand the 8D, right, the 8 disciplines, but where does the A3 portion come from?
So A3 came from the Toyota pioneered practice of getting the problem analysis, corrective action, and action plan all on one single sheet of large or A3 sized paper. This hybrid version works really well for SAFT.
Okay, cool. Thank you, Jill. That was a great walkthrough of your 8D A3. So now I just want to move on and spend a few moments to talk to the fact that you are a certified 6 Sigma black belt, and you could probably deliver a week-long training session, and maybe you're up for paid engagements if any of your audience are interested. But perhaps for now, you can just provide a quick overview.
So there are 2 primary methodologies in Six Sigma, and both do get used here at SAFT. So DMAIC is one of our most commonly used methodologies for existing operations. So it starts with define, then measure, analyze, improve, and control. DMADV is used when creating a new product or service from scratch, with design and verify being the fundamental differences. My biggest takeaway for Six Sigma is that while the improve section is the most important to the customer of the project, having really solid define and measure sections with customer buy-in are critical to setting up the rest of the project. Without knowing and measuring the problem, it can't be improved or controlled. Now, it's always amazing to me when we can use DMAIC here at SAFT with projects in this low volume, high mix manufacturing environment. Problem solving works regardless of volume.
Yes, it does, absolutely. In talking with some of my other clients, Jill, there's another trend to kind of blending lean initiatives with Six Sigma methodologies. They will have one thing in common, and that's to be effective. They have to have good quality and easy access data. So removing paper, data collection from their operations is foundational to solving these problems and improving the processes.
Yeah, applying the lean principles to process improvement is a natural expansion for manufacturing. Identifying wastes, like time wasted waiting for a computer program to respond, is often the first step in a continuous improvement process.
Okay.
So SAF started with shop view. Oh, sorry.
No, I was just going to say, yeah, can you tell me a little bit about your journey with ShopView, Jill?
Yeah, I jumped ahead on you.
That's okay.
SAF batteries started with ShopView in our smaller X6T line. The primary goal was to provide a robust and scalable material traceability and product identification solution, and it was a really successful first phase.
Okay, so you now own the full suite of our digital factory modules with a focus on, you guessed it, moving away from paper records and making data work hard for you. What I'd like you to do is kind of take us through your IT systems and record keeping before you implemented ShopView, and then we'll come back later on in the conversation and show you where you're going.
So this is a snapshot of our data storage when chaos started. And yes, that's about 40 information systems that were all deemed critical at one point in time. I am not going to admit to the number of paper records that were part of our shop traveler. So each of these systems were not maintained in a sustainable manner. So they're supported by a series of people part-time. As a result, routine maintenance and advancements of the systems rarely occurred. Data review occurred manually when someone has the time or the desire to review the data, and in most cases, that only happened when a problem had been detected at the end of the line.
Okay, what is the legend for the color codes on these circles, John?
So the orange color is time domain data, so that's great quality process data, but it's often, as you can see, siloed and almost impossible to align with paper-based transactions. So the pink blobs are spreadsheets. They're a historical favorite data and analytics tool.
Yes, they are.
Purple are our databases with our cell data, and those are fairly interconnected, but not really. The cyan are databases with our electrode data. The dark blue are databases with other miscellaneous formats. And the big black hole in the center are our paper records that support process execution and data collection. Now, this data is okay for audit purposes, but it's not readily usable in support of continuous improvement activities.
That's a fair statement, fair and accurate statement. So as most of our audience probably realize, right, the shop traveler is perhaps not the best medium to support effective recipe control and process control. So remembering that 20% chance of humans doing something wrong metric that we looked at earlier, what workflows, Jill, have you put in place to chip away at those gaps?
So let me provide a quick overview of how we make a battery, and then we can look at some specific examples.
That would be great.
So what we're looking at here is a bottom-up simplified diagram of the materials and processes that go into making a cell destined to go into a battery with the addition of a lot of control electronics. So starting at the bottom with raw materials, we receive those items and then combine them into a mix or ink, which is coated at precise thicknesses onto either aluminum or copper foil. So we coat both sides of the foil, so the material runs through the coater twice. Then the coated material goes to the calender, where we increase the density by decreasing the porosity of the coating. Because we're limited by our coating speed, we coat many lanes of material so that we can coat as wide as possible. And to make that multi-lane coating work in the cells, we slit the material to width and then send the anode and the cathode to the winder. Now, at the winder, we combine this with separator, and then we edge fold to create a single current path. The edge folded wind then goes through 9 various welding and handling operations to make it into a finished dry cell. The welder was a really fun item to integrate with ShopView's digital instructions package, because we have 10 cells running through a single operation in what is technically a single piece flow, all at the same time. So from there, the cells get inspected by our quality department, and then they go off to the filler, which is our last stop in materials traceability. All the operations past filling are to be to the finalized cell as far as parts go.
Okay, I know that is certainly an overly simplified kind of bottom-up view, so, but thank you. It helps set the stage. So let's take a look at a couple of recipe and kind of process control workflows in the field, and that you've migrated kind of shot view to be your point of execution, process and recipe control.
So this photograph was taken at the mixing phase for creation of a batch of anode. So ShopView uses our bill of materials as it comes out of our ERP to determine a list of parts and quantities needed for a production order. So the users open the ShopView issue components tool as directed in our digital instructions for each material to issue. Now, these can be issued during setup or during the run, depending on where they go in our process specification. The users select the part number and then the description of the component they're issuing, and then they scan the lot number of the material, and then either enter the quantity or, in the case of weights, click Read Scale to auto-populate the field. Now, since mixing involves several additions of critical materials and the amounts of those additions are important knowledge, we've used digital instructions to show conformance to our mixing recipes. We've actually prevented an untimely addition of material through that cross-check.
Okay, great. So this is an example of eliminating one of those 20% opportunities of doing it wrong, both in following the recipe and actually avoiding manual translation errors, right, of transferring the scale readings.
Exactly. Error-proofing the process and collecting accurate data. So other error-proofing examples integrated into our ShopView digital instructions are which solvent addition to validate against which, and that can change the conditional path the process needs to take. So for those conditional paths, ShopView will send a yes/no request via API to our internal ERP system. And if the answer is no, you need to stop, it'll tell the user why. So for example, the lot number is not listed as the correct part number, the material is on hold for analysis, the material is expired, or that the quantity that we want to use is more than what's available.
Okay, so in summary, ShopView's component control ensures that the SAF team uses the correct parts in the correct quantities, and actual consumption is recorded in real time to support your full traceability.
Right.
Okay.
So this is a screenshot of our user interface using direct digital instructions. So on the left-hand side are our sub-operations. Now in the center screen, we're getting feedback on the issue materials and subsequent dependent parameters, such as process specification error tolerances. So when the material is issued, we prevent users from deviating from the process and issuing components before processing product. And there are both hard and soft error validations. Users can also see how much quantity is still required and how much quantity has already been issued per part. So coating weight is one of our key process parameters for this operation. And while we control the coating thickness of the mix placed on the foil, it's the weight of the coating that is the critical measure. The weight of the coating directly corresponds to the capacity of the finished cell. Each foil roll is slightly different. We're ordering aluminum and copper foil in the single-digit micron range, so the variability of the foil thickness is unescapable. So we measure an 8-inch sample of foil at the beginning and end of each coating run, and then we use that data to determine how much a 1-inch disc of foil will weigh on average in this run. So ShopView actually calculates this data and determines on the fly the nominal weight of the coated disc, so that when the operator enters sample weights using inspections, the inspections pass-fail accordingly. This way, we've automated the calculations of disc weight and coating weight requirements and applied pass-fail to sample weights, simplifying these operators' jobs.
Excellent, excellent. Simplifying operators' jobs. So here's another quick example of work in progress inspections. What is this technician doing here, Joan?
So Neil, this is a rheometer. It's a laboratory device used to measure the way in which a liquid, suspension, or slurry flows in response to applied forces. We'll do several of these readings throughout the mixing process, so that's perfect for recording and inspections in ShopView. The point of inspection feedback to the plan is invaluable. ShopView can prevent the next activity or require approval to take an alternative process specification path.
Okay. You also use this WIP inspection and parameter data collected from PLCs to deliver your inline SPC, right? Statistical process control charts. What are you looking for?
There are many operations where a level of variability is acceptable, but monitoring these trends can allow our users to make equipment setting tweaks during the run. So in this example, we're coating the A side and B side of an aluminum substrate to make cathode. The operator is looking at the gap settings for the coating and deciding, based on the coating weight sample results and trends, if they need to increase or decrease the gap between the substrate and the coating roll.
Okay.
So in this run chart, you can see that the coater started out under specification, and that widening the gap added more thickness and thus more coating weight. The operator overshot the nominal and has brought the gap down again. So at the bottom of the run chart is a suggestion of the gap required on both sides of the system. The operator takes this into account with their own experience of how the coater runs and may or may not adjust accordingly. Our goal is to give the operator live data in order to make that determination. So our next phase for this operation is planned. We're going to integrate the real-time coating thickness data from our beta source gauge to give the operators further information for their decisions.
Excellent. I'm sure my team's looking forward to working with you on that.
So the biggest thing with my quality background is to integrate the quality review and posting to our ERP system. And that makes it easier for the downstream area to know when a material is allowed to be used. Control of non-conforming product is really important to the eventual quality of the end result. So we implemented a certification for quality operators, and ShopView doesn't allow winding of the product without passing quality review.
Excellent. So I remember, and I'm sure the audience does, the map of the systems and record keeping solutions that we looked at earlier. I'd love for you to share with us where you're going, if you don't mind.
So this is where we're heading as our future state. So much of the phase 2 ShopView MES just went into production this quarter, and we do have several activities left to complete.
So what are the circles within the cell plant ShopView MES, big green circle?
So those are the solutions that ShopView has replaced. So remember, a portion of our business case when investing in ShopView was to streamline our IT infrastructure. Collapsing these guys all into the ShopView MES means that we don't have to maintain those subsystems anymore.
Okay. I also remember that reducing those data silos and leveraging APIs has been a big focus of the project too.
Yes, so if the circles are touching at the circumference, then we're using APIs and connectors to execute effective workflows between our specialized point solutions and ShopView, so our system of execution on the production floor. We're using APIs because we're knitting together several pieces of software. If one changes or the policy behind it changes, we can update the API involved without having to reintegrate.
Yeah, APIs are critical in business solutions these days. Make data work hard for you and keep the interoperability going. So Jill, tell us what's next for the Chaos team.
So there are corporate-wide cross-functional continuous improvement teams being formed with the focus on digitization. We're hoping that the Cockeysville team could be the nucleus of that digitization effort. All of the other sites are committed to 50% of an operations person and 20% of an IT person to run digital improvement projects. Cockeysville has dedicated 4.5 people to this effort, and I think it's paying off.
Oh, it undoubtedly is. So Jill, thank you very much for your time today. We're not quite done yet, but I did want to say that I've learned a lot about continuous improvement, and I appreciate you providing some context around the methodologies that really work well for the SAFT team. But before we say goodbye, I wanted to share what is coming up on the racing scene.
Yeah, so earlier this year, the FIA announced a groundbreaking electric GT category. So they explained that the governing body wanted the new electric GT class to be relevant to the automotive industry.
So as a racing fan and an employee of a battery supplier that will be heavily involved in this EGT series, what are going to be your challenges?
So the biggest challenge is, how can I attend as many races as possible?
Of course.
But the main technical challenges for the EGT series will be fast charging technology. So in F1, pit stops average about 2.5 seconds.
Yeah.
The aim here is to have a battery-powered racing series where we can recharge the car during a pit stop instead of trading one car for another halfway through the race.
Okay, so I did a little bit of research. I don't own an electric vehicle, but I do know that a typical Tesla charger takes about 8.5 hours at 7.7 kilowatts. So what's the target within this race series?
So the goal here is a 5-minute pit stop with a 700 kilowatt charge.
Wow, wow, quite the challenge, quite the challenge. Okay, Jill, well, thank you again so much for joining us today. We enjoyed your insights into continuous improvement, battery technology, and of course, motorsports. Thank you so much.
Thank you, Neil. I enjoyed it.
Thank you, everybody. And please feel free to reach out to myself if you have any questions or you'd like to connect with Jill directly. Appreciate taking your time out of the day. Take care.